So that graph we were looking for in the warm-up, where we were walking around the bridges of Königsberg and we wanted to cross every bridge or every edge exactly once, we would call that an Euler path. I'm just going to make a note here. This is pronounced Euler, right? Not Euler, not like Bueller. So an Euler path, or sometimes called an Euler trail, is a walk in a graph such that every edge is used exactly once. And an Euler circuit is just a special type of Euler path that starts and ends on the same vertex. So if we look at some examples, you can see that some graphs have Euler paths and others don't. That Königsberg graph probably doesn't, or it seems like it doesn't. We weren't able to find one. But if we played around with these other graphs for a little bit, we would find that some of them have Euler paths, some have Euler paths and circuits. A circuit is an Euler path. And some don't. Some have neither. In this one here, this works. So I could go start in the lower corner. We'll use a different color so it's easier to see. Then go up and go to the roof of this house here. Maybe come back down across the diagonal, up to the other corner, across the top, down, up to the middle, down to the corner, and over to the edge. So we started here and we ended here. We can see from the way that I highlighted it that we didn't cross every edge exactly once. So this is an Euler path, but it's not an Euler circuit because I started at one vertex and I ended at another. So this has an Euler path, but not circuit. Okay, now what about this second graph here? We could play around with it a little bit, we could try. So maybe start up here, come down, over and up. Maybe try to repeat that again, come down. But here we're gonna have a problem. So we can't come up here and use this last edge, or over here and use this last edge without getting stuck and leaving one edge out. So this is an example of a graph that has neither. It has neither an Euler path nor an Euler circuit. This one here, let's go back to pink. Let's see what we can do here. I'm going to start at this vertex, come up and down and across. And I'm going to try to, oh yeah, let's maybe, well, we have to be careful here because I was tempted to come back up here, but if I were to try to come back up to this corner that I started in, I'm going to run out of edges. I'm not going to be able to leave again. So I'll leave this edge for last. Okay, so I come back down, maybe go around the triangle at the bottom and across, come up, and finally back up here. So in this case, my starting and my ending point were the same vertex, and I crossed every edge exactly once. This makes this an Euler circuit. If it has an Euler circuit, it automatically has an Euler path. That path is that circuit. Okay, and so in this last example, we can try again. We have, let's see, right, I don't know, we start somewhere. Maybe we'll try to start here and go up around this triangle and maybe the other triangle as well. Come across and down and over. I see already I'm going to have a problem because if I go up, I'm stuck. If I go up and across, I'm stuck. So this is another example of a graph that doesn't have an Euler path or an Euler circuit. Right? And you could try some more and make sure that it wasn't just a bad decision on my part, but that actually it didn't exist. And the question is why? What do all of these graphs have in common? So I'm going to give you a minute to try and play around with it. In the notes, there's this graph, and you can start playing around with it yourself, maybe draw some examples, and see if you can figure out what makes a graph have an Euler path or circuit.